Here's reading guidance for 12-7 and 12-8. So we'll start with 12-7. All right, the fun stuff, finding theoretical probability. Again, this is the probability of what should happen. Our solar system's 8 planets. Yeah, I hate when they got rid of that other one. In order of least to greatest distance from the Sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Again, we're missing Pluto, makes me sad. You will randomly draw one of the names of the planets and write a report on the planet. Ooh, fun. What is the theoretical probability that you will select a planet whose distance from the Sun is less than the Earth's? So, total possible outcomes, 8. Favorable outcomes, well, there's 2 of those that are nearer to the Sun than Earth, Mercury and Venus. Remember the Blue's Clues song? Love that. So anyway, reduce to 1/4. Again, all fractions must be reduced. The probability of selecting a planet whose distance from the Sun, again, is 1/4. What is the probability that you will select a planet whose distance from the Sun is greater than Earth's? Well, again, since this isn't compounded, we didn't, it's not Alderaan, we didn't like blow up a planet or anything. There's still 8 planets. Well, maybe that Pluto thing, right? And whose distance from the Sun is greater than Earth? Well, after Earth, we have Mars, Jupiter, Saturn, Uranus, Neptune. So 1, 2, 3, 4, 5. And so that's 5 out of 8, and that does not reduce, so 5 out of 8. Still Miss Alderaan. Find the probability of the complement of an event. Now we know that word complement, again, from our work with sets. So it's the opposite of it. The rest of the other stuff that you didn't, for the stuff you didn't want. In a taste test, 50 participants are randomly given a beverage to sample. There are 20 samples of drink A, 10 of B, 10 of C, 10 of D. What is the probability we'll not get drink A? So again, there are 50 altogether. 50 drinks, right? And so is that it, right? So 20, 30, 40, 50. Yep, there you go. And number of samples of drink A, there are 20. So reduce 2 out of 5. Now, again, the complement is not drink A, right? So you can do that by just, you could do all the rest of them, the 30 out of the 50, right? Or you could take 1 minus the probability of A. Either way gets you there. So let me write that again. You could say the probability of not A, so that'd be, probability of not A or A prime, and that's going to be out of the 50, there are 30 other drinks that are not A, right? You got to add them up here. There you go. And so that reduces to 3/5. The other way to do that is to take the number 1 minus this probability, right? And plug that in here, and you still get 3/5. Either way gets you there. I personally am kind of partial to this way, but alrighty. So your read and got it here is suppose a test is repeated with the same number of samples of drink A, but more of other drinks. What happens to probability of not drink A? Well, there's a lot of mathy stuff here, right? It will be 1 minus, and X is that additional that goes down here. So there's 50, and more of them. Otherwise, you could say basically it's probably going to increase, right? It's going to be a bigger number that you're going to, of the other. So, a topic related to probability is odds. It says describe the likelihood of an event as a ratio comparing the number of, should we say favorable? Whoops, that word disappeared. Favorable and unfavorable outcomes. So odds in favor of an event. The things that you want versus the thing you don't want. So on the bottom this time is not the possible outcomes. It's the thing you want versus the thing you don't want. Or you could say A over, the prime of it, right? The complement of. Odds against, flip that thing over. Okay, what you don't want on top of what you do want. So, we have a spin over here. 1, 2, 3, 4, 5, 6, 7, 8. Loads of fun, right? What are the odds in favor of the spinner landing on a number greater than or equal to 6? So favorable, 6, 7, 8, right? Greater than or equal to 6. There's 3 of them. Things you don't want. 1, 2, 3, 4, 5. There's 5 of those. So your odds are 3 to 8, right? In favor of getting a number that is 6 or greater. And you can write it this way, 3 to 8. That's another way to do it. So what are the odds against the spinner landing on a number less than 3? So odds against this time, okay? Odds against. So let's take a look at that real quick. So odds against, so what I don't want versus what I do want. And I want a number, so I want a number less than 3. So that's going to go on this side because it's odds against, not odds for. Landing on a number less than 3. Well, that's 1 and 2. There's 2 of those, right? And there are, how many others are there? There are 6 others, right? Of things that I don't want, So, and we can reduce an odd just like a fraction. So that's really 3 to 1. Again, some folks write it 3 to 1. Either way is fine. But again, this one's against. You got to pay attention to what I'm asking for on the quiz or test because I will try to trick you with this. Okay, so experimental probability, like we discussed in the vocab, is you have to run an experiment. What actually did happen versus theoretical, what should happen, right? And the cool thing is, if you run an experiment enough times, the experimental usually approaches theoretical. And I've done this when I teach 7th grade. I make everybody flip a coin, and by the end of the day, we flip that thing like 10,000 times, and it's pretty funny how close we get to 1/2. So anyway, after receiving complaints, a skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds no defects in 992 of them. What is the probability that a skateboard selected at random has no defects? Again, this experiment looks like a random experiment. So total number examined, number with no defects. So 992 out of 1,000. You could reduce the fraction if you want to. You could write as a decimal. You could write as a percent. And I might ask you for any 3 of those on my quiz or my test. So suppose the manufacturer inspects 2,500 skateboards. There are 2,450 found with no defects. What is the probability a skateboard selected at random has no defects? Right, the probability is a percent. So, again, that gives us out of 2,500, right, inspected 2,450. And you can divide that out, 0.98, right, which becomes 98% in the end. So, again, if I ask for a percent like that. So, more fun with experimental probability. You ask 500 randomly selected households in your town if they have a dog. Of the 500 households, 197 said they have a dog. If your town has, so again, that's the sample, right? If your town has 24,800 households, about how many are likely to have a dog? So what you want to do is find, again, using your experiments, number surveyed, right? Number that own a dog, 197 out of 500, which is 39.4%, or as a decimal, 0.394. Multiply that times the total households. And you can assume there's 9,771.2. You gotta know what the 0.2 does because that's gross. But again, about that many households that you would expect to have a dog. So let's say a manufacturer inspects 700 light bulbs and finds that 692 of them work. There are about 35,400 light bulbs in the warehouse. How many would you expect to work? So, straightforward stuff here. We have 692, right, out of 700. Now, another way to set this up would be to set it up as a proportion, right? And you would say X out of 35400. That'd be another way to do it instead of doing the whole decimal thing. It's going to get you the same answer. And you can use your fish method or whatever you learned in last year in order to solve this. And you're going to find that you get about 34,995. I think the exact number is, I think it's 34,995.4286, right? So obviously you can round that down because it's 0.4. So here we'll have the reading guides for 12-8. As a review on here, probability of mutually exclusive events. So events that, whoops, didn't mean to do that, whoopsie. Oh well. Yeah, that's stuck there now. So anyway, let's scoot this down. Probability of mutually exclusive events. If A and B are mutually exclusive, you just add the 2 things, right? But if there's overlap, this is important. If there's overlap, then you add them together and subtract the overlap piece right there. So, and again, we'll do some examples like this. But remembering, mutually exclusive, things that don't affect each other, no overlap. Things that have overlap. And again, this gets back to your idea. If we do it as a Venn diagram, which I know how much you all love Venn diagrams, right? If there's an overlapping possibility here, so if I had a bunch of, if I had two sets of numbers and they had an overlap in the middle, that's the piece you're going to be subtracting out with that. So if I had 1, 2, 3, 4, and over here in the number set I had 4, 5, that 4 is an overlap. And that probability of 4 you're going to have to, subtract out would be the idea. Mutually exclusive and overlapping events. Suppose you spin a spinner that has 20 equal sized sections numbered from 1 to 20. What is the probability you spin a 2 or a 5? Now, that 2 or 5, non-overlapping, right? So it's a 2 or a 5, not a 2 and then a 5. That's a big distinction to make here. We're not talking about compound here. So anyway, probability of 2, right, is 1 out of 20. Probability of 5, 1 out of 20. You just add those two together. 2 out of 20 or 1/10. Probably spin a 2 or a 5 is 1 out of 10. So, again, mutually exclusive here, right? Let's see here. What is the probability spin a spinner that is a multiple of 2 or 5? Now you got to do some thinking, don't you? Since a number can be multiplied by 2 and 5, such as 10, the events are overlapping. So that's where we get the overlap here. So, multiple of 2, right? So we got to think about that. What numbers on there, by the way, are multiples of 2? We're going to have 2, right, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? And then you got to think, okay, of those, which are multiples of 5 also? Well, 10 and 20 are, right? So there's your overlap piece. So you want to take multiples of 2, right? That's half the numbers, 10 out of 20 right here. And then those that are 2 or multiples of 5 rather. So that's 4. What am I missing here? 4 out of the 20. Hang on a sec. Yeah, I'm forgetting multiples of 5. There's also 5 and 15 are other multiples of 5. So there's 4 of those that are multiples of 5. That's here. And then go back and we subtract out the 2 that are overlaps. This and this. And then we end up with 3 out of 5 is the possibility once you simplify. So here we suppose you roll a standard number cube, right? What is the probability that you roll an even number or a number less than 4? Okay, so let's think about that. Even numbers are 2, 4, 6. That's it, right? Or a number less than 4. Okay, so numbers less than 4 are 1, 2, 3. So this is A we're working on here, by the way. So we gotta we're gonna have to subtract it because you have some overlap, right? We have some overlap. So numbers that are less than 4. Yeah, 1, 2, 3. So we have some overlap right here. So we're going to subtract that out. So what this looks like is probability of numbers that are 2, 4, or 6, right? An even number. So that is so that's probability of even, right? And then we add to that probability of less than 4, right? And then you subtract from that probability of getting a 2 because that's our overlap piece. So that's it in words there. So numbers, probability of even is going to be 1/2, right? And the probability of less than 4, well, that's also 1/2. And then minus the probability of 2, which is 1 out of the 6. And let's do the math on that. So that gives you, 1, right, minus 1/6, which is the magic 5/6 there. So that's how we got that one. If you're confused by that, go back and listen to it again. Give it a go here. So B, right, what is the probability that you roll a 2 or an odd number? Those are mutually exclusive, so you don't have to subtract. So probability of getting a 2, right, and then probability of an odd number, well, that's an odd number. Those are 1, 3, and 5. Pretty limited there, right? So probability of 2 is 1 out of 6, and the probability of the other is 1/2, right? So what do we got? 1, 6, and 3, 6. Is that right? So 4, 6, which reduces to 2/3. There you go. Alrighty, now on to independent events. A little bit easier, I think. So Um, Suppose you roll a red number cube, right, and a blue number cube. What is the probability that you roll a 3 on the red and an even on the blue? So 3 on the red, 1 out of 6. Even on the blue, 1/2 of them, right, that are even, 2, 4, 6. And then you just multiply those two. So this is the tough thing in this test, is to remember when do you multiply and when do you add. So look for that mutually exclusive stuff in some of those for the adding part. And again, multiply it out, simplify, and we get 1/12. Let's say you roll a number cube and a blue number cube again, so red and blue again. What is the probability that you roll a 5 on the red and a 1 or 2 on the blue? So we have probability of 5 on the red. Well, that's 1 out of 6, right? And then a 1 or 2 out of blue. So that's there's 2 out of the 6 there. And again, remember those don't affect each other at all. So 1 times 2 is 2, and 6 times 6 is 36. So yeah, I was just looking there at the bottom here, and that's definitely not right. That reduces to 1/18. So anyway, there you go. That's definitely the better answer. That's not correct. Alrighty, so now this time with replace. So here we've got events that independent and dependent, right? We talked about in your vocab there. The last set would have been, obviously independent because you don't scratch the number off 1 when you roll the next one. Now selecting with replacing, that makes something independent again. So if you take it and put it back, it's like starting all over. So they're independent. You choose a tile at random from the game tiles shown, right? You replace the first tile, then choose again. So you replace independent. So probability of something with a dot, right? There's 1, 2, 3, 4 of those. And the probability of then getting a dragon, there's 1, 2, 3 dragons, 3 out of the 15. And then you multiply those two and reduce, right? Don't forget that function, you didn't have to even reduce here. The probability that you will choose a dotted tile and then a dragon tile is 4 out of 75. So what is the probability that you randomly choose a bird, then after replacing it, a flower? So again, we know there are 15 here, right? And there's going to be 15 the second time because I'm replacing it. So I always like to think about that denominator first. So choose a bird. How many birds are there? There are 1, 2 birds, right? So 2 birds. And again, we replaced it. Then you replace and get a flower. So is that a flower? Looks like 1 flower, right? Is that right? Yep, just 1 flower. So 1 times 2 is 2. 15 times 15 is 225. Hey, that's the answer. Tried to give us in the last one. I think they had those answer keys backwards. So that's not right. So 2 out of 225. Again, with replacing, the denominator stays the same the second time. Alrighty, moving along. This time we don't replace. Going to use the same set here, right? Suppose you choose a tile at random from those. You choose a tile, rather, without replacing. So notice without replacing. This is going to change the denominator. And this time you wanted to choose a dotted tile again, 4 out of 15. Second time, though, there's only 14 to choose from. And 3 of those are still dragons. Multiply. And going to reduce 2/35 after you simplify. So let's say in problem 4 here, what is the probability that you will randomly choose a flower? Okay, so let's do this. We know the first time there are 15 tiles. If I don't replace, there are 14 the second time. That's important. I always do the denominators first. So you're going to choose a flower. So flower, just the 1 flower there. Without replacing it, then a bird. And there are 2 birds, right? So that's 2 over... well, let's go ahead and find out what that is. Just a second. 210, which reduces to 1 out of 105. There you go. Alrighty, so again, without replacing, watch that denominator. A little more fun with compound events here. It says here 1 freshman, 2 sophomores, 4 juniors, 5 seniors received top scores in the school essay contest. To choose which 2 students will read their essay at the town fair. That sounds like fun, doesn't it? 2 names are chosen at random from a hat. What is the probability a junior then a senior are chosen? Now here's the thing. This is without replacing because you don't choose them and throw them back in line and choose them again. Not fair. So we have probability of getting So a junior, there are 4 of those out of the 12, right? So there were 12, 6, 5. So yeah, so we have a total of 12 possible. Is that right? 6, 5, yeah. Oh yeah, then forgot the 1 freshman. There we go. So 12 reduced to 1/3. And then a senior afterwards, there's only 11 people this time. So 5 out of the 11 people. Multiply, and no need to reduce this time. Alrighty, so this time, it says in problem 5 was the probability that a senior then a junior are chosen. So if we take just a second here, I'm going to pop in that information from that chat from that section real quick. There we go, in case you couldn't remember it. So again, there is 1, 2, 3, 4, 5, 6, 7, 12, right? Yep, 12 people. So we're not going to replace them. So first time 12, second time 11, because we don't replace them. So this time, probability that a senior, so how many seniors? There were 5 seniors out of the deal. And then a junior, and there are 4 juniors. So that's 20, right, over 132, which I believe reduces to 5 out of 33. A little bit of thinking here. Is junior then senior different from senior then junior, and explain? No, it's the numerator that makes the difference here. Now, if you did, junior then junior, right, that kind of thing, but then your numerator is going to be affected, but they don't. It's not affected in this case, so.